How would we use the error bound, this thing right here, to prove that the Taylor series for e to the x converges to e to the x no matter what x is, as n goes to infinity, that this goes to 0? We need to figure out m is the key. To do that, it's a little tricky because technically, these derivatives of e to the x were all e to the x. Technically, e to the x or e to the t, if you want to think of it as a t, gets very large very rapidly as t gets bigger. So initially, to do this, we need to put a bound on the size of the input there. Consider the interval, say, from minus infinity to some fixed number b. Over this interval, the graph of e to the t stops at some point when we reach b. I drew b here so that it's positive, but it could be negative. Because the graph looks like this, I can take the m to be e to the b. You want to think here of b as being a fixed number. We're going to do this analysis for a fixed number b. But b is arbitrary. I said it could be negative, it could be positive, it could be a humongous positive number. The fact that it's arbitrary, and I'm going to prove convergence over an arbitrary interval like this, will imply that it converges for all x. The fact that b is arbitrary. It doesn't matter how big it is. Over this interval, capital M is e to the b, which is a fixed number. So the absolute value of the error is less than or equal to m e to the b over n plus 1 factorial times the absolute value of x to the n plus 1. But the absolute value of x is a constant. You want to think of x as a constant here as well. The only thing that's a variable is n. We have constants there and there. We're choosing to be ahead of time. It could be some fixed but arbitrary number. We're saying let x be in the interval from minus infinity to b. A is still 0. The key thing is these are fixed numbers. N is the variable. And no matter how big those numbers are, this still goes to 0 as n goes to infinity. The book does give an argument for why that's the case, but let's just believe it with numerical evidence. For example, if I take b to be 10, then m is e to the b, which is a large number, by the way. E to the 10th is about 22,000. And take x to be, maybe a fairly large number as well, maybe 8 or something. Large compared to really close to 0. Enter that and compute values of m times the absolute value of x to the n plus 1 power divided by n plus 1 factorial. I don't really need the absolute value thing there because x is positive, but bear with me here. What happens now if I plug in values of n? This is the syntax for how to take an expression and plug in this case, n equals 2, sort of after the fact. There's what I get when n is 2. Is that a big or large number? It looks big. It is big. When n is small, the absolute value of x to the n plus 1 is winning out over the factorial. But as I keep increasing n, what happens? It's getting bigger here at first. Getting bigger, getting bigger. Yeah, it's still getting bigger. What if I get a lot bigger, friend? Now it's got smaller. It went from 8 something times 10 to the 6th to 4.74 times 10 to the 6th. Then it's 20. I'm down into the thousands. If n is 30, I'm down to small numbers. If n is 100, Yes, very small. If n is 1,000, it's saying stop. I don't want to do it anymore. Okay, so small, it's rounding it to 0. It's not a proof. You could try other values of x and b. You'd still get something that gets small as n gets large. The factorial is dominating the power. So that proves, therefore, p to the n of x approaches f of x as n goes to infinity for all x in the interval from minus infinity to b. But again, the b is arbitrary. Therefore, Pn of x approaches f of x for all x. Again, as n goes to infinity. Since b is arbitrary. It doesn't matter what b is. I can go from this step to that step. I had to pick a b, a fixed b, to be able to come up with an m. But once I've done that and come up with this argument, relying on this error bound, then it is valid. Of course, this begs a question. How do you prove the error bound theorem? Again, the book does do that. I'm not going to do that. The answer actually involves using properties of integrals of all things. I would encourage you to look at it in the book.